I'm very excited to be here and share some of our work with you. And special thanks to Omar for continuously reminding me we have heard enough about your control plane. It was published widely, and we want to hear something else and touching more on the operational aspect of the network. So I try to touch upon those aspects. So I'm going to talk about lessons learned from designing, developing, and deploying B4 over the last few years. So probably most of you know, Google runs two separate backbones. The first one is B2, that's the traditional old backbone that faces the internet, even though it's growing faster than the internet today. And the second one, that's the B4, that's the topic of discussion today. It does not connect to the internet. It only connects data centers across the world. But B4 carries more traffic than B2, and it's currently growing at a faster rate than B2. And you can kind of see the growth over the last few years. So B4 is SDN controlled. It uses OpenFlow as the mechanism to control the switches from external servers. So last few years, we've been mostly focusing on control plane and trying to improve its availability so that we can move more and more critical traffic from B2 to B4. B4 is cheaper, but it started as an experimental network. And over the years, it has matured, and we have moved a lot more critical traffic onto B4. So remaining challenges at this point are mostly operational. It primarily stems from scale, as you can imagine, which warrants for automation. But in trying to automate, we are also running into issues because of heterogeneity. Like B4 has 2 to 3 flavors of fabrics, and it pairs with different data centers. And there are, again, 2 to 3 different variations of data centers. And each campus is slightly different from the other. So that's where automation becomes challenging. So before I dive deeper into B4, I want to give a little bit of background on the team that built it. So we are a network infrastructure team, part of Google Platforms organization. And we are tasked to deliver networking solutions for Google's data centers. So over the last decade or so, we've been delivering data center solutions like Watchtower, Freedom, and the new one called Jupyter. And WAN, of course, before we'll talk about more, and network virtualization solution like Andromeda that powers Google's cloud solution. Along with that, we also build a lot of infrastructural pieces like Bandwidth Enforcer, gRPC that powers all of these. So in this talk, I'll focus on B4. However, a lot of infrastructure is shared across all these solutions. So many of the lessons learned are also shared across these solutions. And we have published a few articles recently among various solutions. And many of the lessons published there also apply to B4. So let's start with why we built B4. We already had one backbone. Why another backbone? And why we chose SDN? So Google's data centers are located in physically diverse locations across the world to serve 2 main purposes. One is, of course, to serve traffic closer to the user, and also to replicate traffic for fault tolerance. So you can see there are 2 distinct classes of traffic that we need to address. One is user-facing, and one is inter-data center. And the characteristics of these 2 traffic are quite different. So the inter-data center traffic does not have a smooth diurnal pattern like the internet-facing traffic. And also, it's much larger in volume. We noticed most of the Google servers do not really communicate with servers outside Google. So they mostly communicate amongst themselves. So the inter-data center traffic volume is much larger. And also, the services that run over these have different kinds of SLO with respect to throughput, loss, and latency. So we need to provide that kind of SLO for different kind of SLO for different services. So with that, we figured building a separate backbone may be more useful and more cost-effective. but since we're talking about large volume, what happens to cost? Does cost really reduce, per unit cost really reduce as we increase the volume? It happens for compute and storage, but not naturally for networking. The basic problem there is it's quadratic by nature because it's pairwise. That does not help reduce the cost. At the same time, managing the network is also an expensive part of owning that network, and each individual equipment is traditionally managed by operations folks, and we cannot scale the operations team linearly with the growth of the network. And also there is a lot of complexity involved in deploying different vendor gears. They all expose different API, and managing them is challenging. So we thought SDN can answer these problems. So we moved to SDN-based solution. So as we all know, it separates the smarts from the embedded devices. So we can roll out software features at different pace than hardware. And more importantly, we can leverage Google's compute for doing the smart pathing. And also network management becomes easier because of the homogeneity of the APIs that are exposed. So we manage a fabric rather than individual devices. And last but not the least, it would be more cost-effective in terms of throughput if we can centralize the pathing engine, and we can run very advanced multi-commodity, multi-objective flow algorithm and can use the network optimally. So today I'll give a brief overview of the architecture and how it evolved and how we use traffic engineering. And I'll briefly touch upon the benefits that we have enjoyed so far. And I'll mostly focus on lessons that we learned from deploying it. I'll describe 3 lessons in 3 key areas that we focus on: performance, availability, and scale. So before started from pre-SDN days, actually. And it was very traditional, it was built of traditional routers, which hosted protocols and silicon in the same box, like the traditional routers do. So the first step, we took the protocol out of the box and put them in the high-performance servers, and we put a thin layer of OpenFlow agent in the same boxes. And then we put the SDN controller in the middle to send the packets back and forth and compute flows and push them to the switches. As you would observe, we still have one-to-one correspondence between protocol speaker and the silicon. So it's still very compliant with the old traditional routers, and you can upgrade one at a time, and you can still communicate with or peer with existing network. So that was part of the requirement on day one. So for fault tolerance, we added a second SDN controller, and we housed them in 2 data center buildings. Typically, data centers have at least 2 buildings, so for fault tolerance, they're broken into 2 equal halves, so that even if one building has issues, we would have half the network working with one SDN controller. So this whole thing is called a site, and that's our unit of management. That simplified the management model significantly. So at this point, we have parity with traditional network, and these protocol speakers speak traditional protocol amongst themselves and to the other sites. So once the stage is set, we started looking into reaping the benefit of SDN, which is the central traffic engineering. So we built traffic engineering as an overlay layer on top of BGP ISIS-based traditional network. We want to do per QoS traffic engineering because we want to do different SLO for different types of service. And we want to use the network optimally with max min fair bandwidth allocation. For overlay, we are putting the traffic engineering flows in the same switches as a higher priority flow that OpenFlow allows. And only when TE flows are not there, it can fall back to BGP or ISIS flows. So the BGP ISIS flows serve 2 purposes here. One is fallback, of course, and also BGP is still used to peer with the data centers. So the architecture kept evolving. We added a central traffic engineering server that takes demand and topology as input and also gets the prefixes for the clusters, and it produces traffic engineering pathing solution. And there are a few other global servers that helps traffic engineering engine. There's a bandwidth enforcer piece that I'm not going to describe much, but it collects the demand from all servers across the world and feeds it to the T server. And SDN gateway communicates with all sites through a TE app. It collects topology and prefixes and programs the sites. So what did we gain from this design? So at a very high level, throughput, of course, went up. So as you can see, this plot shows 1 year of throughput gain over shortest path. So on regular basis, we get about 20% improvement over shortest path. And I picked this period particularly because we had bandwidth crunch towards the end of 2014. We could not deploy more capacity even though we needed. So the benefit of traffic engineering solution was actually higher at that point. It went over 30%. And the other benefits that we observed, we are rolling out software changes much more often without taking any capacity hit. We don't need to drain anything. We can just upgrade the T server without touching the switches. And most of the time, you don't really need a switch change to change the pathing policy or optimize the algorithm. At the same time, you can also upgrade the hardware, probably at a slower pace. We rolled out 2 or 3 generations of hardware, but it was decoupled from the software upgrade, so it's still under the same software architecture. So now to the lessons learned. So the first lesson I'll describe is in the area of performance. And this was actually caught in lab very early in testing cycle, and we're lucky that we caught it early. So our initial simple-minded assumption was we will use OpenFlow protocol, and we'll send flows and flow programming requests and packet IO requests sequentially from the controller to OFA. That's what OpenFlow 1.0 standard kind of specifies. So we'll send them in sequence, and switch will program them in sequence, so the system will be in consistent state throughout. But this is what we found out. As soon as we started scaling it to as little as 1,000 routes. So SDN controller is fast, and that was the main purpose of using those. On the other hand, the OpenFlow agent, which is in the embedded device, is much slower. So we started seeing queue buildup on the controller side. What made things worse was these flow rules were generated in bursts as output of some flow computation. And then the packets were queued behind a burst of flow requests. And on the embedded device, flow programming takes longer because it involves programming the hardware. So packets are delayed even further on the switch. And OpenFlow allows only one connection. OpenFlow 1.0 allowed only one connection between server and the OpenFlow agent. So as a result, we saw head-of-line blocking by the flow rules for packet IO. So packets were delayed, and the protocol started timing out. And timeout would trigger more computation, more flow programming, and we'll get stuck in an unstable state. So to address this, we did some improvements both on the controller side as well as the embedded side. So we introduced 2 queues, one for packets and one for flows, and strict priority scheduling between these 2 queues. On top of that, for flows, we did a flow control between OpenFlow agent and OpenFlow controller so that the number of outstanding flows are limited. So that would limit the delay seen by any packet that comes up. And also we started implementing queue drop discipline on the server side, both for packets. There's no use sending very old packets. And flows we can probably coalesce. If the same flow gets generated 5 times from 5 computation, we only need to send the last one. On the OpenFlow agent side, OpenFlow agent initially was not asynchronous, so we made it asynchronous. And on the switch side also, we separated out the packet I/O path from the slow flow processing path. So the combination of these, we got a more scalable and more stable system. So next one would be on availability. So availability probably means different things to different people. And talking of availability, first I'll touch upon lack of availability, which is outage statistics. So I want to clarify these outages are not externally visible. These are mostly masked by internal redundancy, but we do take them very seriously still. And you can see we would take feedback from outage history, and we have taken it into account in our next generation design. So the plots at the bottom shows the growth of before in terms of number of sites, in terms of number of open flow domains, and BGP routes and TE paths. And on top, you see the outage statistics broken down into different categories. So there are different types of outage. For the one that we would like to focus on is the blue one. That's the unstable mastership. As you can see, through 2012 to 14, the number of outages caused by this kind of root cause, it increased steadily as we increased the size of the network. So this is one kind of outage we took seriously and we reacted to it. So in 2015, when we rolled out the new architecture, you can see this family of outage disappeared. However, because we were rolling out new architecture and we were migrating, basically we replaced the whole network with new hardware, new software, and new controller architecture. So there were some outages, but this particular type of outage went away. So our initial naive design will have n+1 redundancy. So one building would have one SDN controller and the other building would have the second one. So if one building goes down, we would still be running. And the control plane actually spans across the two buildings. So what we observed in practice, the control plane network between these two buildings is not always stable. As a result, often there was partition in the control plane, and both controllers would claim themselves to be masters. So gateway would see two masters. Even sometimes OpenFlow agents would see two masters. So that would cause a lot of topology churn and unstable pathing, and reachability would be affected. It would be black holing packets till this is mitigated. So to address this, we broke the site into multiple domains. Now we have 4 domains. Each domain is independent and within the same building. And we have 4 such domains for redundancy. But within each domain, we have independent set of controllers, and we have Paxos-based robust master election. So we haven't seen any more multi-master kind of issue after we deployed this. And also, as an effect of this, we removed the single point of failure. So there are 4 different domains, and each can fail independently. This has improved our availability by a big number. And the third lesson I'm going to talk about is on scaling. As you can imagine, we've been deploying more sites and deploying more compute per site. So we need more capacity per site. So how do we deal with that? We can deploy larger switches, or we can deploy a lot more switches. So each of them have their own pros and cons. More switches means the global control plane would be larger, and that would have one aspect of scaling. And larger switches would mean a switch failure would take down larger capacity, so the bandwidth hit would be larger. So SDN is kind of a natural solution to this kind of problem. So we can build hierarchy naturally with SDN. So we built small flow fabrics. We call them one SDN domain, and we provide abstraction. So you can see each flow fabric is abstracted as one router or one BGP-speaking entity. And we call it a supernode. And all the links between supernodes are called supertrunks. So we can run protocols at that granularity. And also, also TE would see only fewer nodes and fewer links. So that improves topology scaling by a factor of 100 or so for us. On the other hand, for hardware failure, it's still the small, tiny chassis that fails. And if we need to repair, we need to troubleshoot, we can still do it at the granularity of the small chassis. So this also improved availability as a result of such smaller granularity of repair. So in conclusion, we have seen significant benefit from SDN, particularly in terms of throughput improvement, and also decoupling hardware upgrade from software upgrades. Lessons, the 3 lessons that we kind of highlighted today. One is regarding system performance. So flow control between different components running at different speed helped improve stability. In terms of availability, robust reachability of the control plane is key. And for scale, hierarchical topology abstraction has helped us significantly. So that's all I have. We published some of the before work in recent conferences that will give more context of this work. And thank you very much for having me here.
Questions? Got a time for just 2 or 3 questions, I think. So we got one, Patrick. We got someone here, or we can repeat for you the.
So with the domain-based arrangement. With the domain-based arrangements, you said TE is only on the master nodes, right? Do you do any TE within the domain? In the class topology?
So within the cloud topology, we do implement WCMP in order to realize that TE padding that's given by the T server. So T server gives path at the granularity of sites, and it also gives fine-grained if you want to split on between the supernodes, if you want to do uneven split. And that's realized by the domain controller by implementing WCMP. So that's some flavor of TE.
So, go ahead. So OpenFlow has been working for you for many years. Since gRPC has been announced, do you see any value moving away from OpenFlow to uncover gRPC rather than trying to program every flow, just provide data model-driven programming to the device?
So gRPC, I feel, is more generic, and OpenFlow has its own limitations. So we started with OpenFlow with a vision that we should be able to swap the embedded device at any point and use any OpenFlow compliant box. But if gRPC becomes more standard, so we can do the same thing with gRPC as well, right? And I think some vendors are exposing gRPC now.
I talked to some people at Google bringing to ATF.
So I see 2 different approaches. In the morning, Microsoft talked about So I kind of see 2 approaches. In the morning, Microsoft talked about using the current protocols and things like that, modify a bit for that scale. You come from a different angle of building organically from the scratch, building your own network. So 2 different approaches. Like if I were an enterprise, what you would suggest, which direction I should take? Use the existing one, tweak a bit for the scale, or take this approach which is diametrically orthogonal to what I have today?
So we kind of have a hybrid approach. We kept the traditional protocol as well, just that we didn't tweak it for optimization. We built our own on top of that, just because we could, and it gives better optimization for us. But that said, a centralized approach is not necessarily non-standard. So there are some standards where you still have a central TE. But the API between T-server and the devices, we have our own proprietary, but there are some BGP-based standards where you can still propagate the padding information to the BGP speakers, which are the nodes.
Yeah. Sorry, I think I would appreciate if you can clarify again. You went with a hierarchical approach for scalability, but how much of the scalability approach is hiding topology and details from the controller, or whether the controller is still doing low-level path computation, I guess, without necessarily, I guess at the lowest level of the hierarchy, I guess, is what I.
Yeah, so we have different levels of controllers. So if you go back to the picture, we have the domain controllers, which knows the detailed topology of the domain, which knows the exact flow inside the domain. And there is also the T server, which is global, which need not know about the failures within the domain. So its computation is also done in hierarchy.